And so our next presenter is Dr. Constantine Frangakis. I think he's going to share his slides, and I'm going to give a brief introduction. Dr. Frangakis is a professor of biostatistics at the Johns Hopkins School of Public Health with joint appointment in the School of Medicine. His expertise is in causal inference methods, and specifically in partially controlled studies. He developed a statistical framework called principal stratification, and this method allows to address the problem of partial control, essentially to find the degree to which the effect of the control intervention on the main outcome is explained by the effect of the intervention on the activation of intermediate causal pathway that are not directly controlled. So this method has been applied in a variety of clinical disciplines and with different trial outcomes. So thank you, Dr. Frangakis. Please, let's hear your talk. Thank you.
First, thanks very much, Gayan and Dan. Ravi gave a very good discussion about what is the state of the art in methods for estimating, I would say, models for individual level effect heterogeneity. Of course, he did say that you can use these methods to estimate also other features of, like group based heterogeneity. And this is really what I'd like to discuss. So let me start by the question that motivated this. A few years ago, in collaboration with psychiatrist Kostas Liketsos here at Hopkins, I was helping on analyzing a clinical trial for the effect of citalopram versus placebo on lowering agitation symptoms for people who had Alzheimer's. And let me see here. I'll only focus on what is important for my talk here. This was a trial of, let's say, 190 individuals, and it tested giving citalopram to half of them versus just psychosocial intervention in the other half. And among other outcomes, there was an overall outcome of response or no response at the end of the trial. And here I have the percent. So there was a response of 40% in the drug arm and 26% in the other. So there was a difference in about 14% of the individuals who responded more in the drug arm. Now, this, from my understanding and my memory, was received relatively well, but somehow the physicians wanted to see if there are groups or subgroups, I'd say, of the trial that had a larger effect. For example, 30%. The overall, the 200 people had an effect of 14%. And what if there were some subgroups that had a much larger effect, like twice that, okay? One reason was that it was known even before then that citalopram had some side effects in the heart rhythm. And so the clinical, I would say, logic was, or the clinical reasoning was that physicians would be more comfortable giving or suggesting the drug to a subgroup if they knew that the effect for that subgroup was or would be much larger than just 14%. Okay. Now, how would you go about finding subgroups that have a larger effect? We are talking about using covariates here. Now, for demonstration, it is useful here to consider two covariates, each of which is categorical. The first is what Dr. Liketsos termed affective function, which measures basically the history of mood disorder, if there were prior histories, depression, if there is background past anxiety, irritability, etc., versus executive function. Basically, if a person can have attention, or if there is problems with motor skills, planning, disorganization, etc. So, because some of them I mentioned with a positive sign and some of them with a negative, just overall, these were, let's say, scored 1 point extra whenever a person had a problem with any of these issues in the parentheses. Okay, so that's why this can go from 0 to 7 and this can go from 0 to 6. So to give you an idea of the distribution of these two covariates, because each one goes from 0 to some large number, let's say of not very large, even 7 level, and 6 here, there are a person can be in any one of these cells, and and for example, in this cell, EDS1 and ADS3, there were 5 individuals assigned to the control, to the drug, and 1 individual who was assigned to the placebo. So the red is the number in the drug and blue in the placebo. I think so. Let me see. Yes, red is in the placebo, in the citalopram, sorry. So if one wants to estimate effects for subgroups, you can think, first of all, what is the finest subgroup that you could have? Of course, you have many other covariates, but as I said, this is for demonstration. So the finest subgroup you may have is a cell here or a cell here. So it's a particular EDS and ADS level, okay? That's the finest subgroup, and you can say, okay, I'm going to estimate the effect of citalopram versus placebo for all of these cells, which are 7 times 8, 56. That's not possible from what you see, because reasonably possible. First of all, because there are some cells that have 0 people in one of the treatments. And even if they don't have 0, there are cells that have a ridiculously low number of individuals. So we cannot actually go cell by cell or profile by profile and estimate the effect like we do for the overall trial. Yeah. That's the main problem. Okay. There is a part of the talk that also discusses another example, but I'm not going to go over that example for HIV unless I feel I need. Okay. So we are a little stuck with the approach of going cell by cell, but even though we are stuck, I want us to consider the case where we are able to estimate the effects within each of these cells, because I want to see if I could do that, how would I then find the groups of individuals with an effect, let's say, larger than 30% or with 40% or whatever. Okay? So my goal is, before I go there, is to assume for the moment that we know the effect of the citalopram versus placebo for each of these cells, that we know the effect here, there, and I want to find I want to find something very concrete. I might have said that I want to find if there is a subgroup of individuals who have an effect larger than 30%, but there may be many subgroups that have an effect 30%. There may be zero, but there may be many. If there are many, I want to find the largest. Okay, it makes sense, okay? I would like to find what's the largest subgroup that I can characterize who have an average of a large effect. So there are two large things here. I want to find a large subgroup that has a large effect, the largest subgroup that has a large effect. And I have to put the threshold for it. The largest subgroup that has, let's say, 30% effect. Okay, so going back here. So I'm going to do first a thought experiment for getting the theoretical answer if I know these effects for every cell. Okay. So let's see. I'm just going to skip that. First of all, I'm going to consider like a toy thought experiment. So where there are 4 cells in a trial, not 56. There are just 4 cells. Each of the 4 cells is equally populated, quarter. And I have a problem with this. Yes. In this column, I'm giving us the known effect for this cell, that cell, I mean profile, okay? Profile of individual, for this profile and for this profile. Okay, here they are. Now, the average of all of these, I don't know what it is, but I'd like to find what I said before. I'd like to find the largest subgroup that has an effect of 30%. So here you may notice that they are not ordered. This is 10, 30, 80, and then it goes back to 0. So how would I go about finding the largest subgroup with a large effect? it makes sense, and it's actually the correct theoretical answer, to first sort or reorder the profiles of individuals. So we reorder the profiles of individuals by the effects for each profile. So I reordered them here. 8 is first, 30, 10, and 0, okay? And then I'm going down the rows. That's very simple, okay? So if I want to have the largest group that has an effect of 80%, that's just profile 3. Because if I start putting some people from any of the other profiles, I'm going to dilute this effect, okay? That's why I start from the top. Then if I start including people from profile 2 that have an average of 30%, and let's say I include them all, the average drops to 55% because it's the average of these two. And now I have 50% of the people of the trial. If I want to see what happens when I include more of the people in the trial, I would have to start including from the 10%. And the overall average drops, okay? And then when I include everybody, it drops to 30%. So what's the largest subgroup of the trial that has an average effect of 30%? It's all the trial. Because if I look at all the trial, it has 30%, okay? But let's say I want now to do this for other thresholds. What I want to do is I want to order the profiles. Here I put the largest, the profile with the largest effect, 80. Then I put the next profile that has a profile specific effect of 30. Then I put a profile that has a profile specific effect of 10, and lastly 0, okay? So with this curve, where I put here the profiles ordered by their specific effect, I can put in the vertical axis the average of the profiles that I am including in the trial. So if I just include 4, the fourth, I have 80%. If I just include the third and the fourth, I know from before that the average is 55. So I mark here 55 for the third, and I mark 40 for the second and 30 for the first. In other words, what I have done here is I have ordered the profiles on this axis. How many profiles are there? There are 4. Order them by their effect specific to their profile only. That's how I've ordered them. And on these axes, I plot the average of the profile that I'm considering. Let's say for profile 3, I mark 55 because that's the average of profile 3 and everything above it. This is the, how would I say, effectogram I would call something like that, because it gives me for every threshold that I want on the left, on this vertical axis, it gives me what profiles I should be including in the not in the trial. The trial is over. What profiles I should be including in my recommendation. So if I want only people who have 80%, it's only the fourth profile. If I want people who have 55% and over, it's profile 3 and 4, etc. Okay, so I hope it's clear what it shows, and it is correct. It's correct. It answers exactly, in fact, the question of what is the largest group that achieves an effect of red or higher here. Okay, I'll come back to that in a moment, but this is the theoretical answer. Now, this is the theoretical answer if you have like 4 profiles, okay? And now we go back to our problem, because we said that, well, we don't have just 4 profiles, we have 56 profiles, or if we include also age and other covariates, we have many profiles. And these profile-specific effects are not easily or reliably estimable in order to do this graph. But it's important for us to have this graph in our minds. Okay, so what do we do? One approach, which I would call the standard approach, is to estimate a model for the individual outcomes. For example, I think like something like what Ravi suggested, either with parametric or non-parametric or semi-parametric methods. So what does that mean? If the outcome here is response, yes or no, I can do a logistic regression looking at the drug treatment and estimate the response in some simple model with the ordered covariates, and also do the same thing for the placebo. Okay, this will give me a way to predict, not to know, but to predict the difference between these two, which I think Ravi called the individual effect, I think. Ravi, if you hear, just tell me what you call that, so we can also...
Individualized.
Individualized treatment effect.
Yeah. I said individual cannot be estimated, but individualized can be modeled.
Yes. So this is a model. So we can model this, and remember what we want. We want here we want something very specific. Remember the subgroups. So one thing we can do is to take these as if they were the true effects and do what we did with the simple 4 profiles. What did we do? Remember, we took the individualized effects, we sorted them, we ordered people. Okay, let me show you again. We ordered the profiles, and then we went from right to left, computing the averages of the effects for everything that is included from left to right, okay? So I'll show you what that means. So let's suppose we do that, take the predicted effects, individualized effects, and order them over here. And I'll tell you what we'll put on these axes in a moment. But first, if I include, I'm ordering them from small to large, okay? And I start from the largest of these effects. Let's see where it is. It is over here. That's the largest. That's the largest such value. For that value, there are 5 people who have that value as we have predicted it. There are 5 people here. Now, go to those 5 people. There are 3 in the drug and 2 in the placebo. Go to these 5 people and estimate the non-parametric treatment effect. In other words, go to these 3 people here, find their average response. It's ridiculous, right? There are just 3. But let's do it, okay? And go to those 2 people, find their average response, and take the difference. That gives you 67%. All right, it's based on 5 people, right? So I'm not going to give much attention to that. But let me start doing this from right to left. That is, let me go now to the next largest value of the predicted individualized effect. And take the average of these and and come, let's say, to this point. What's this point? It's the point where I have whatever they are about, let's say 10, 15, 1, 2, 3, 4, 5, 6, something like 15 here. What's this point? It's the 16th largest predicted value of the effect, of the individualized effect. Here it is. Okay, what do? I take all the profiles, that is all individuals that have a predicted effect larger than this guy's effect, which is 32%. Sorry, which is whatever it is, I don't know. But when I take the average of all of them, it gives me 32%. Now, this may have sounded a little convoluted, but if you see why I'm doing this, remember that I'm looking for a subgroup, a large subgroup that has an effect of 30%. Okay, here is the my desired thing. Why do I go from right to left? And first of all, why am I going from right to left? Because I know that if these predicted values were correct, this is how I should be finding my possible subgroup, going from right to left, based on these ordered values. Okay. Second, why am I going from right to left? And whenever I stop, I'm computing the non-parametric treatment effect? Because these values may be wrong. They're based on a model. So although I'm using these values just to sort people out, but then when I stop and try to estimate the average effect for these guys, who, by the way, are 71 individuals, they are 43% of the total. I don't want to use a model anymore. I want to just, for these individuals, find what's the average for among the subset who are assigned placebo, and what's the average among those who are assigned drug, and take the difference. This is a valid estimate of the effect for this subgroup. So I have found at this particular instant, I have found a subgroup. Wait, where is the subgroup? That's the subgroup. It's the individuals whose predicted individualized effect is larger than or equal to these guys. Okay. I have found a subgroup. How many is this a large subgroup? It's pretty large. It's 43% of the individuals. I have found these 71 people that when I look treatment and control with no model anymore, the effect is 30%. That's why I'm pointing to this, okay? And in fact, if you see, you may ask, why did you stop here and not here or there? All of them have an effect larger than 30%. This is the largest one, because if I move a little bit further down to include more profiles, I drop below 30% for the non-parametric effect, and I never rise up again. So that's pretty special, okay? Now, if you see, I understand one has to be trained a little bit to understand these graphs, and so I don't intend to, require that. But I just want to tell you this, that the beginning of this graph is the top estimated effect profile, which is not to be trusted because it's going to be based on just like 5 individuals. The bottom one is everybody. This is the bottom one. Everybody is to the right of this. So if I look at the effect for these guys, it is the effect for all the trial. And in between is what I'm actually trying to understand, okay? Gayen, can you give me my time? How much would I need more?
At least 10 minutes, and then there's
another time for
questions. Yes, thank you.
So let me, since I have it, sorry for this, but okay. So I do want, this is from the paper that I cited, and it may be showing this in a more interesting way. This profile, this plot that I showed you earlier is the profile with the red dots. Okay. And one nice thing about such a plot is that you can put in the horizontal axis the percent of people that are included to the right. So if I look, for example, at this dot here, this says here 91. This means that there are 91% of profiles to the right of this. 99.
Kostas, yeah? I don't think we're.
Yeah, we're still seeing the.
Oh, I see. Yes.
You need to refresh your.
Oh my God! Yes. Okay. No. So Okay, hold on.
It's okay. We're sending you to personnel for retraining on PowerPoint afterwards.
Okay. Okay. That's good. So I'm saying this is the plot in the paper, and I'm saying that one nice thing here is that you can order people, as I said, based on their model estimated. This should sound alarms wrong. That's what it means. But it's okay to use it to order people. So this dot here has a 91, which means that there are 91% of individuals to the right of and including that dot. And this dot has a vertical value of 20%. What does that mean? It means that if I include everybody here, all these people to the right of this guy, which is pretty many, like 91%, the empirical non-parametric effect, how do we get this? We get these people here, whoever they are, we throw away our models, and we take who is under citalopram. Okay, what's the average response? Who is under placebo? What's the response? Take the difference, 20%. So although all of the trials individuals give, this is all 100%, give an average of close to 14%. This is what I said at the beginning. You can find a subgroup of 91% whose effect is 20%. Okay. All right. So let me do this switching again. All right. And we said, hold on. I don't just need retraining. I just need training. So let's see. I want to go to my, that's it. Okay. All right. Let's see. Okay. All right. So by doing this here, let's see where we are. Yeah. So by doing this graph, we can read off that yes, there are subgroups. This is the first. There are subgroups of the trial that have an empirical effect, and I emphasize the word empirical because we switched from a model effect to an empirical effect, okay? There are, if you don't know how I did that's one thing to ask later. But again, so yes, there are subgroups that have an effect larger than 30%, and the largest one seems to be these 71 people, or 43% of the total. If I wanted to ask, are there subgroups that are have an effect of 40% or larger? Can you see where there? I go here. Let me see. I go 40%, 40, 40, 40, up. So there is these and all of these, especially this, and I say all of these, I mean all of these guys, averaged have an effect of 40%. But they are very few. How many are there? 1, 2, 3, 4, 5, 6, 7. There are 7 profiles only. Here they are. Okay. So this is what I'm showing here. I'm showing that if I'm looking for, this is the map of the covariates, ADS, EDS, and the yellow is showing where are these subgroups. It is this yellow combined subgroup on the top that has an effect of 30%, and this is a pretty large subgroup. Okay, if in the end that when I said, okay, let's look for the 40%, which is this is the identified subgroup, but it's very small. Okay, so let me show you for the moment what we have done with an individualized model for the effects. We use that to order people by their supposed effects. And then when we ordered them and we got groups, we estimate empirically now the effects for these groups. This assures that our claim that this group, blah, blah, has an effect of 30% is correct. And it's not affected by the model that we used here. You may say, what is this? Is this magic? No, it's not magic. It is just using a model for ordering the individuals, okay? Now, you may ask though, wait a second. If when I find the average here, and I get the empirical to be 30%, and let's say I just want to check what would I get if I had averaged the model-based effects of these guys. If I had averaged the numbers of these. I'm not doing this here. I'm doing the non-parametric. But what happens if I would average these numbers? Suppose I get something different, like I would get 50%. This would mean, indeed, that the model is wrong. But if the model is wrong, can I try to modify it? And the answer is yes. And how would you modify it? Well, let me show you this. This sorting is, as I showed you before, and it's based on the maximum likelihood of the estimates. Again, it could be based on semi-parametric, machine learning, whatever. It's based on estimating these betas by MLE, assuming the model is correct. Now, this is when I jitter a little bit the beta. What I want you to see is that, when I use the MLE and I ask what's my largest group that has 40% effect, we saw that it's pretty small, right? But because the model is wrong, and I know it's wrong because I compared the effects, I can ask for a different beta, for a different model fit that that shifts this to the left and includes more people. And in fact, there is a different beta that, you see, gives now for 40%, it gives a larger means smaller to this side, effect. And here it is, okay? This is what I showed you before with the beta based on the maximum likelihood. It gives the best, subgroup for achieving 40% is 8%. But by asking what is then telling me about what is the best model for the beta to do this task, then I get a much larger effect. A much larger subgroup that has an effect of 40%. You may say, wait a second, we learned that the MLE is the best estimate. No, we learned that the MLE is the best estimate if the model is correct. If the model is wrong, then a different estimate or a different member of the model, a different beta, does better the job I want, which is to use a wrong model to estimate the group effects. Okay. I don't want to take more of time from possibly thinking or for my next colleague, but I just wanted to tell you that I just wanted to reach to this overall slide that what we have done here is basically we have taken a model for individualized treatment effects, and we saw how we could use it for, in this case, for ordering the values to create subgroups, which we then used to empirically re-estimate the effects so that we can be valid. However, there was this second or third phase of this, which is, the first is the ordering, the second is the empirical averaging. The third realization is that once you realize that the model that you are using shows evidence that it is wrong, you can alter the model in order to better achieve the original goal, which is find the largest group that has these effects. And actually, therefore, this can cycle in some sense, as you can understand, but it is it's an interesting approach we have found to use and actually improve models for estimating a clinical question. Okay? So that's what I want to say.
Absolutely, thank you. This is very, very interesting. And I saw there was an example of the actual trial, right? Besides the one that motivated the question. The method was applied to a different trial.
Oh yes, yeah, to different trial and to the to the HIV also. Yeah.
Yeah. Thank you.
Well, I have one question for Constantine. You have contrasting methods of defining a subgroup. What is the best way to test for truth with regard to the subgroups that you create? Is it to look in an independent data set, or are there other ways to determine the best way to characterize a threshold for effect, a given threshold for effect?
So I would say, from what we have done with Vivek, my collaborator on this, that you take your trial, and it has to, it seems it has to be of the order of like 100 and more, like in order to do that. And you sample, you can sample with replacement, otherwise you get stuck. And with that sample, I don't say you train, but you estimate what these subgroups are for achieving, let's say, an effect of 30%. And this gives you a rule which then you can go and apply it to the original. I mean, you could do also splitting if you have enough, etc. But the definite need is to account for possible overfitting. What we did find that if you ask for a subgroup that gives an effect of 30%, the largest subgroup gives an effect of 30%, and you do that, when you apply the rule back to the original trial, it gives you less. So it can give you like 35%, sorry, 25%. You ask for 30, you look for the rule for 30, but it is actually for 25 because because there is kind of a little bit too involved, this estimation. The more individuals you have, the less this difference will be. But what we do ultimately is we find what is this, let's say, discount factor, and we say, okay, all right, since I have to go larger. So if I want 30, I will shoot for 35. Right. And there is this factor goes smoothly and doesn't change like from, dropping to 5.
So it's an iterative, if I understand you correctly, it's an iterative process in which you can either do it on split data sets or develop a descriptor for a subset that has a high response and then test it independently on another data set.
Or half of the same or something like that, Yes.
Great, thank you.